Howdy y'all. Today I will be presenting the electronic properties of interfaces in oxide materials for my OREU final update. My name is KHANG Nguyen. I'm an undergraduate student at Texas A&M University at the Department of Material Science and Engineering. For my acknowledgements, I would like to thank Dr. Michael Demkowitz and Isabel Cantu for organizing this research opportunity, and Dr. Blas Uburuaga and Dr. Elizabeth Peterson for their mentorship and guidance. I also acknowledge Dr. Sambit Das, Professor Vikram Gavini, and Professor Fani Motamari for developing the DFTFE code and assisting with installation, and Dr. Pratik Dolabai for providing the oxide structures for the simulations. So our motivation for this project is largely based in the interfaces in oxide materials, which have many potential applications, including nuclear materials, semiconductor materials, and high temperature ceramics. As you can see in this figure over here, what we're mainly interested in is semi-coherent interfaces. And this interface semi-coherent interfaces occur when the lattice mismatch between the structures are too high, and this causes defects. Our objective is that we want to understand the electronic and atomic structure of these very large interfaces and defect patterns. Classical models can capture the atomic structure of these large systems, but they can only do it without the electronic structure. Our objective in this project is to bridge the gap and model the electronic structures of the interfaces and relate their structural defects to electronic properties. As you can see on the right here, this is a atomic structure that has been classically generated, and based on the termination that is generated on, it shows two different types of interfaces and two different types of defect patterns. What we want to see is how the electronic structure varies at these specific defect patterns. So density functional theory code. So this code, it calculates the electronic structure of materials based on the quantum mechanical properties of the electrons using the many-body Schrödinger equation. Traditionally, it can only be done on a small scale, 1,000 to 5,000 electrons, because of computational limitations. This means that we can't really use this for our very large interfaces where we want to capture the entire defect pattern. In order to kind of get around this, we're going to be using DFTFE. This is a code that is developed by the Computational Materials Physics Group at the University of Michigan, and this performs real space DFT computations using finite elements on a local basis. This process of using finite elements on a local basis allows for large and fast, accurate, and large-scale DFT calculations, 50,000 to 100,000 electrons, 10 to 20 times faster than other approaches. And this will probably allow us to calculate the electronic structure on these classically generated atomic structures. So DFTFE scaling. Most DFT code has cubic scaling for the cost compared to system size. This essentially means that if you double the system size, then the cost is going to multiply by 8. DFTFE has quadratic scaling up to 30,000 to 40,000 electrons. This means that before 40,000 electrons, around there, when you double the system size, then the cost of the computation is only going to multiply by 4. For systems larger than 40,000, DFTFE focuses on numerical methods to reduce the prefactor and improve scalability. This figure on the right is showing you the process of a self-consistent field iteration to solve for the electron charge density. As you can see, it just makes an initial guess, calculates the effective potential, and solves the KHANG equation in order to calculate the electronic density, which is then checked to see if it's self-consistent based on a tolerance, and if not, then it redoes the iteration. And these iterations, they go until they reach a certain convergence value, which you set based on your tolerance. And often the process of this convergence is based on the mixing strategies that you use. So some challenges that we faced with DFT-FE were the installation and running issues. And this was because of kind of difficulty finding demos that were analogous to our systems. Our systems being here on the right, these are the ones that we ran so far. The smaller system on the left is a system of FECR03, I believe. And this system is a coherent, it was a semi-coherent interface that was strained in order to become coherent, just as like a quick test. And this larger system on the right is the, it's essentially the larger basis of what the system, the smaller coherent system was created by. And this is a grain boundary between two materials, creating a semi-coherent interface. Another challenge that we had was the limited GPU hours that we had on Perlmutter. Perlmutter was the supercomputer that we were using, and when you use Perlmutter, you have an allocated number of GPU hours, which essentially means like the time that you're allowed to do computations on Perlmutter's GPUs that they allocate to you. And this made running large-scale systems like our grain boundary over here very difficult, because in order to even run it, we have to do debug tests, and those debug tests take up a lot of GPU hours on their own, because the system is so large that it requires a certain number of RAM, a certain amount of RAM to run. The last issue we were having was getting the self-consistent field iterations to converge. And this essentially means that there's a specific value that is shown after each field iteration, and we saw that this value was often oscillating and instead of converging. And we believe this might be due to the low dielectric constants that are usually seen in these types of interfaces. And essentially what that does is it causes charge perturbations at these structural defects, and that can affect the charge density a lot and slow down the calculations a lot because of the structure. For analysis and conclusions, the process of calculating the electronic structure is still a work in progress, but we expect with the DFT-FE's capability that we'll be able to get significant results once we optimize the mixing methods past the standard mixing methods and use more advanced ones for the convergence, and we optimize the parallelization parameters for GPU efficiency. Thank you very much.